They did not know the carriers and so on. The first person who connected macroscopic picture to microscopic picture is, whoever you want to look for something fundamental, you go back to Einstein. Einstein's 1905 paper in Brownian motion is the first paper that describes the connection between macro world and micro world. But what are the assumptions in Einstein's paper? So Einstein calculated, I have a set of independent particles, particle motion between two consecutive intervals independent, displacement during time t is s, and is unbiased diffusion. The probability to go step s is the same as minus s, and there is a finite jump probability or distance that you go. With this assumption, he says, I start with a random walker. How far does it go? And he said, well, the time it goes after n is the sum of jumps from I to n Si. All I know is that there is a mean free path, there is an average jump length, and if I divide it by average velocity, I get a mean free time. Again, stochastic, microscopic picture. You calculate what is x squared, the distance square, you calculate what is the mean square displacement, you take this sum and square it. What is interesting is when you square this, you have cross terms. And if the jumps are independent, this should be 0. From one jump to the next, there is no correlation. Crucial now result that Einstein uses is central limit theorem. He doesn't call it central limit theorem. I know over time, always name of things changes, and that's one thing you have to be careful. If I have a set of n random variables uncorrelated, and is n large, central limit theorem tell you converge to the Gaussian limit. So what is probability to be at distance x times t is given by this. This exactly look like the equation I showed you here. So the reason Fourier law is so powerful is the Green's function solution for it applies to random processes whenever central limit theorem applies. And central limit theorem is an important theorem of statistical statistics, and that's the reason it's so powerful. But again, you have to pay attention when this doesn't apply. But what is interesting is Einstein has this mean square displacement goes with time, but now he can connect this macroscopic quantity to the microscopic quantity, which is the average distances they go divided by square divided by time. So when I guess you show this type of approximation, you automatically are putting this type of central limit theorem there. The first person who questioned central limit theorem was Paul Levy. Paul Levy, pure mathematician in 1935, asked a question. Consider a random walker. Each step is identically distributed random variable with power distribution function p of x. He asked a question when probability Pn of x to be after n step at a position has the same shape as p of x. So he asked the questions mathematically. The sum of random variables when each one is a Gaussian is always a Gaussian. That's what we know. He asked, beyond Gaussian, are there other distributions that have this property, scaling? And he found that this is the function with exponential absolute value k to a gamma. And this gamma could be anything between 0 and 2. All of these obey this property that after n scatterings, the power distribution, probability distribution function will have the same form as individual. If gamma is equal to, that's a normal diffusion. That's what we understand by Gaussian process. That's what the Brownian motion is. But he had gamma divided by smaller than 2 also mathematically obey this. There is a slight problem. Gamma is smaller than 2. The mean square displacement is infinite. Physicists know infinite never happens in real world. It's only in other worlds we can see that. So for a long time, people said this is a mathematical, interesting thing, but doesn't apply to physics. Why this happens is that this when the gamma is smaller than 2, this function has power law tails, not an exponential tail. And these heavy tails, that's what caused the problem. But since 2000, there has been a lot of work, what is called anomalous diffusion. There is this one physics report, this is in Physics Today. Beyond Brownian motion, fractal generation of Brownian motion is rich fizzled and so on. This was part of the things that was popularized with the chaos theory and the dynamic system. People started seeing things. It's one of those things. There's something doesn't exist. You can explain everything around your world with existing theories. Somebody come up with a new theory, then suddenly everything is explained by the new theory. People for hundreds of years didn't see it. What are the places? Diffusion of a tracer in a turbulent flow. That was one of the first experimental work of this. Motion of cold atoms. This is more recent. Walking patterns of human beings. People took pictures of people walking in a supermarket. And, when you're in a supermarket, you don't pay attention, but they look at you and they look at the trajectory, and it's not a Brownian motion, it's a Levy walk. Why is it Levy walk? Because, you're looking for yogurt, you go to the milk section, you wander around, you find the yogurt, you take it, then you look for, orange juice, you go to the juice, so you jump, and then you have some random walk next to it. So whenever you have these jumps and random walks, you have what is called Levy walk. Maybe I should show you a picture of this. So this is what I mean. And these days with computers, each one of you can do it. Start a random walker and start at a position and randomly choose a jump, and then random number generator, choose a jump. If the jump length is given out of an exponential distribution or of a power law with a power more than 3, you will get this type of thing. And this is exactly what Brown observed as Brownian motion, and that's what's called regular diffusion. You're at the beginning here, over time you wander around and you diffuse. Here is after 1,000 steps. But if, of course I changed notation just to make sure you're awake. Alpha here is the same as gamma before. Here is a Levy walk with alpha equal 1. What alpha equal 1 means is that you still have a random walk, but you don't, you have heavy tails, so you get a random number, you wander around, but sometimes the random number is so big, you go out of this close vicinity to a new location, and you wander around here. And then random around here, then another jump, and so on. So you have a series of randomness and series of jumps, and this is stochastically very different from this. This has a fractal dimension. This covers the whole plane. This doesn't cover the whole plane. There's lots of things that happen with it. And this is something that you don't see it if you just put a simple relaxation time with 1 or 2 times. This is one of the interesting things about central limit theorem. A lot of the molecular dynamics and so on, you do, oh, this is too noisy, let me average it. I run it 1,000 times. That way of averaging kills some of these. You don't see some of these by definition. People say, but you confuse me. You started with the differential equation, which was Fourier's differential equation. Now you're going to this random walk. I want a differential equation. How many of you really want a differential equation? I guess most people, they don't care. Differential equation is nice, isn't it? At least see the equation, you have a coefficients and so on. Differential equation for Brownian motion is diffusion. Differential equation for Levy is this. So here you have a second derivative with time, with the space. You have a fractional derivative of time with space. How many of you have studied fractional derivatives? At least one person. Why fractional derivative? As soon as you put it, what does it mean? You forget how this was confusing the first course in algebra you took, this d square over d square. People who came out with definition of derivative, I guess at the time of Newton, what was contemporary of Newton who also? Leibniz. He came out in his Leibniz original book, I don't know, from 400 years ago. He said, the same way I defined regular derivative, you can define fractional derivative, and in our future, people will find some good uses for it. How do you define this? It's the same way you define fractional powers. 10 to the power 2 is 10 times 10. 10 to the power 3 is 10 times 10 times 10. What is 10 to the power 2.5? All of you put it in your calculator and give you a number. But how? It's the same thing here. You can define it as an infinite series expansion. So let me now see, I have 5 minutes. Maybe, what are questions? Maybe one question is that all of this nice math, how do you apply it to experiments? So just to tell you how the same phenomena could be seen using different techniques, this is the issue of frequency-dependent thermoconductivity. People like David Cahill started almost exactly 10 years ago, but a lot of work in Gang Chen and others group. They said, when you measure thermoconductivity of materials, especially alloys, at frequencies 0.1 to 1 megahertz, you get a number. You go to frequencies of 10 megahertz, the number is different by 30 to 40%. So they said you have to define a frequency-dependent thermoconductivity. Frequency-dependent thermoconductivity is tweaking to make the Fourier law works, which inherently is an approximation to that means Fourier is not accurate. I skipped some of these. These are raw data. Here is related to pump probe temperature on the surface. This is the delay. You do the measurement at 1 megahertz, 1.8 megahertz. If you fit it with Fourier, you get the black line, and you need 6 watt per meter Kelvin. The same material, the same laser, you just change the modulation of laser to 15 megahertz. You can fit it with this, not exactly as good, but still 3.8. These two are significant. You can believe in it, you can define a suppression function for it, but the question is, but this is fundamental material property. Why every time I change the measurement apparatus, I need to change a different number? You can fit all of it with the solid line. This is a truncated Levy that give you a fraction. This alpha is the same as the gamma before. If it's 2 is diffusive, if it's 1 is the Cauchy, 1.66. That's what we get for this material. UBD is ballistic to diffusive time. A distance is about 3 micron. What it tells you is that in the first 3 micron, the randomness is by this super diffusion. After that is a regular diffusion. Let me skip why you get this. You can explain based on the theory, this 1.66 or 1.65. There is a paper about that. Yes?
I was wondering, this alpha is, are you suggesting it's universal?
It's actually, this is the place that explains it. So alpha is 1 plus 3 divided by n, and n is the exponent of the scattering with respect to frequency. If I calculate tau, scattering relaxation time for phonons versus omega, and omega to the power, you give me the power from that, I can calculate alpha. It's not related to geometry or so on. It's not universal in that sense. But if whenever you have alloy scattering, omega is to the 4, from that you can get this.
This 1.6 now suggests n is 4.6?
Sorry?
Okay.
So 4.6 is the exponent. You put it here, you get v of 1.6 in alpha. So you can calculate alpha if you know omega, the t of omega, tau of omega. Let me maybe the last view graph. What did, yes?
What's the error bar on n here?
Error bar in terms of how well we can calculate alpha.
How certain are you it's 4.62?
This one depends, how you fit this one. But the alpha, we have the raw data, and we can give you 1.66 plus minus 0.02 or so. We can extract from experimental data the fractal exponent quite accurately to within a few percent.
So you have the same accuracy for n then?
Well, to go for, yes,
n.
yes. But one thing I should say is that, again, I'm looking at the temperature on top of a surface. How you connect it to the n relates to, you are assuming there is a single, you are assuming that there is a single omega n, there is a line. In some materials, there are features here and so on. Real life is complex, but the average slope gives you a good idea of what is this. What I really mean, maybe this is the last view graph, is that whenever you study materials, different regimes of transport, here is time, here is root mean square displacement. At times less than 10 picoseconds, at distances less than 10 nanometers, things are typically on the order of ballistic. Distance goes with time, like bullet. At times more than microsecond, and distances more than 100 nanometer, things are diffusive. Distance goes with the square root of time. What we have shown is that there is a range of 3 to 4 order of magnitude in distance and time, where the distance and time go with a fractional power. What is interesting is that these distances are exactly distances of the devices we have. So every electronic device we have, we should not use an effective thermoconductivity. We could to explain one configuration, but if we want to have a concept that doesn't depend on configuration, we should use the right diffusion exponent. Why? It's like approximating this exponent by playing with the coefficient you put in front. That's what is the frequency-dependent thermoconductivity. This is in time, at a steady state, how things change. This is a paper, recent paper by Bjorn. If the films are very thin, the cross-plane thermoconductivity decreases with 1/L. That's a ballistic limit. When the films are more than 10 micron, thermoconductivity can be defined independent of thickness. In the range in between, the thermoconductivity has a L to the power 1/3 dependence. Again, I can define here, and I can define the thermoconductivity, but then every time I change the sample size, I need to choose a different thermoconductivity. Let's use the right scaling parameter. Maybe one last point is that when you see the problem from different perspectives, it tells you something, but there is still something that bothers us for quite a bit. I told you you can get through fixed equation, Fourier heat equation using linear response. Heat flux is proportional to temperature gradient. I just told you that this is not valid. Fourier is not valid. The first impulse is that linear response is not valid. Let's add a nonlinear response. No. What we have can be explained as a non-local heat transport. Heat flux at position x depend at temperature gradient at position x, but also x prime. And this is the memory in a space, and this is exactly the same. As soon as you add a memory, you add this random walk, this Levy behavior. And basically, all the pictures eventually converge. But solving a differential equation with an integral inside is much harder. We have not been able to do this analytically for any samples, but intuitively, this is how the heat flux relation comes in. So there is a non-local behavior. Again, if you do averages locally, you automatically neglect here. Let me, I guess, I wanted to tell you something about Carnot, but let's not to take too much of your time. If you have questions, I can tell you how Carnot derived Carnot cycle. Let me summarize. I told you about heat superdiffusion. There is a Levy flight that happens, but it's truncated. I didn't say too much about it. Something about fractals, which is quite powerful. If something is fractal at length scale of 1 nanometer, even if the device is a meter long, the fractal behavior stays. That's what the scale invariance means. We know we recover heat Fourier law at long scale, so we need to cut it by hand. So that's where the truncation comes in. But temperature profile at this time and length scales, which is a lot of the real devices, are non-Gaussian and non-linear, and you need to look at the superdiffusion as one way to explain it, and I told you how you can measure this, and I didn't tell you how you can go beyond that, but I would be glad to answer any questions. There's a question back there.
You thought that the macroscopic picture of the Fourier law can be connected to the microscopic picture of Boltzmann law with some connectivity like starting from the Brownian motion suggested by Einstein. I have one question. In some models, macroscopic models like the dual phase line modeling of Tizu, we have two time scales, the heat flux relaxation time and the temperature, relaxation time in TZU model. We have
Which model, sorry?
TZU model, the extension to the Catano model, in which we have two time scale.
Q?
TZU, TZU, TU, TU, TZOU.
Yeah. Zoo, yes, I see. So there are ways basically to take the differential equation of Catano and put the relaxation time, certain dependencies to other parameters, so make the equations more complex. If I remember correctly, I mean, Zhu has this book about different ways you can introduce basically some sort of a hydrodynamic effect, or sorry, some sort of causality into the heat equation. And some of these models are called thermal lag models and so on. As far as I understand, again, you know, each of us only see the words the way we see it. I don't see it the same way others see it. The statistics of the how scattering randomized things is not included in that. To get to this type of super diffusion, you need to start with different statistics. You cannot cure it with a differential equation that does not have fractions in it. Really, you need to have fractions, and that's a problem. So people try to approximate it, add a third order term to first and time regimes, spatial regimes that could be correct, but doesn't consider the whole thing.
Yes. So my question was that if these coefficients can be calculated, can be connected to the microscopic picture, but because when we want to calculate these time scales, we verify the results from this microscopic picture with the experiment or some results from Boltzmann equation. So there is, we can't calculate this relaxation that
yes.
as you told.
So I mean, there's two ways to approach the problem. As an experimentalist, I apply a temperature decays. What is the minimum number of parameters I need to explain that decay in temperature? And what we have found is that if you introduce a fractal dimension and you introduce the ballistic to diffusive and the regular thermal conductivity, these three parameters can explain all of the results. The question is how each of these three parameters related if you really can do the full phonon dispersion and the scatterings. As I said, the fractal dimension is related to initial slope. The ballistic diffusive transition can also be explained to the relaxation times and the extent of that. I guess Javi has a paper about this. And the thermal conductivity, that's what everybody derives. So the three can be related to the microscopic pictures. But sometimes there are parameters like this discussion we had yesterday, normal versus unclap and so on. When we measure an experiment, at the end we just measure a decay in temperature. With these three, we can do it. How? I think the temperature dependent of parameters may require some other ways of separating these parameters. But from an experiment, there is not enough information to get more data out of it. With these three, you can fit everything.
Thanks, Adi, for the nice talk. I had two questions. One is, so starting from Boltzmann and relaxation time approximation, you can get your Levy exponents and parameters of your theory, right?
Yes, yes.
And so you don't need to do normal and class separation. You just have a single relaxation. Yes. The other question is, so how do you reconcile? So yesterday you had the talk by Sangyup about the hydrodynamic flow in graphene. So do you think flow in graphene, heat flow is hydrodynamic? Is it super diffusive? What's the...
Very good question. And that's something we have been kind of struggling with in the last 2-3 years. Everything that has to do with 1D heat transport, and even in the thin film, even ultra fast, we can define it using super diffusion techniques with one parameter. When the geometry is more than 1D, and this is the devices I showed you, when I have a heat source on top of a substrate, not the heat only goes down, but also go radially. With the best super diffusion alone, we cannot fit it. So we had to add hydrodynamics separately. So super diffusion is a fraction. It considers the different length scale. It considers the fact that you have long jumps, but it does not consider the lateral transfer of energy from one to the other. And you really need. So that's we don't have a theory. So we can. In one limit, we can solve the problem. In the other limit, we can solve the problem. We don't have a unified problem for both. So I think hydrodynamic is definitely there. But inside hydrodynamic, something I guess maybe I went quickly, if you do pure hydrodynamic, to fit our experimental result, then you still need to use the thermoconductivity as a fitting parameter. That tell you there is something not right, but we cannot put the fractal dimension inside hydrodynamic, or at least not yet.
The higher order moments of the exponents, I mean the 4 and 6 and etc.
Exponent for the
variation of the variance.
No, we haven't.
Because there is as you know, in turbulence and Anderson localization.
Yes.
People started with type of simple one-parameter scaling theory.
Yes.
Which, if you go to high order, you will immediately that there is deviation.
I see.
Therefore, Levy picture is the simplest one. Which
Yes.
can give this just second moment.
Yes, yes.
This is one question. Another question is that how I can imagine that in thermal conductivity, fluctuations jumps from one side to another one. I have some physical problem to understand this. In the random walk, I understand, but for thermal fluctuations.
So two things. First of all, I think you had mentioned a very good point, is that higher order moments could have an information that we need in certain experimental results. We have not done it. And that adds a different type of parameters, which will be good to do. The second question is this picture that I described of a random walk. Random walk for a particle makes sense. I have lots of concentration here. Things move randomly. How I see random walk of heat, I only see random walk of energy. So what I think is there's packets of this local kinetic energy with random that are transferred to the neighbors, but also transferred to distance, and that's what gives the non-locality. And there is enough scattering that I can still define a temperature. But in the limit, when things are very close to ballistic, that's where it becomes an issue, is that I cannot say, here is as a temperature 1, it jumps right away there, and the temperature suddenly changed to temperature 2. So that's where the multiple temperature could come in, and that's where things are harder. Let me give you another example. If I have a ballistic conductor, everybody says, I have a ballistic conductor, temperature in the middle you can be calculated. But by definition, ballistic, energy goes from one side to the other, and energy from this side goes to the other. There is not a single temperature. There is a temperature for left-going packets and a temperature for right-going packets. When you average it out, you get the average of the two. But average of the two does not mean there is a single temperature. There is two temperatures at each point. So the same way, I think, in cases where you have these ballistic jumps, there could be, I don't know if it's the right way to say it, like islands of different temperatures that eventually equilibrate. That we don't see. But I agree there is something about definition of temperature we have to be careful. It's not a local equilibrium anymore, correct? Local equilibrium, I define a local temperature. Now I have something non-local. The question is that temperature, how is related? And that, we put it under the right. So with laser techniques, we have 100 femtosecond time resolution. So time resolution is not a problem. The transducer we use, like a metal layer, the time response of electrons and phonons in that transducer to become in equilibrium, and that become in equilibrium with the layer underneath, that determines our resolution to measure temperature in temperature versus time, and we think is on the order of hundreds of picoseconds. So optically 400 femtosecond. Temperature-wise, we think we can measure temperature with 100 picosecond, 50 to 100 picosecond. And that's enough with lots of electron-electron interactions to define a temperature on the transducer. That's, I guess, also I kind of put it under the rug, but it's very important. I have a material, there may not be a single temperature inside of it, but if I put a metal transducer on top of it and I use the metal as a thermometer, electron-electron interactions in the metal are so fast, I can define a temperature there. So that's not ambiguous.
Wait, I think it's time to move to the break, maybe in the